Welcome to the Dr. Kumar Discovery. My name is Dr. Ravi Kumar, and today we're diving back into another episode of Tribulations. This one is all about the development of antibiotics, and especially the race to bring penicillin to the world during the shadow of World War II. It's a story packed with lucky accidents, genuinely miraculous treatment outcomes, and an all-out sprint to turn a laboratory observation into a real drug. Honestly, it's a fascinating story, and I really think you're going to enjoy this one. And before we get into it, it's important to know this show is for informational purposes only. I'm telling a story that's meant to be fascinating and memorable. And along the way, there are lessons and ideas that can help us think more clearly about medicine and about the future. But none of this is medical advice. Let this knowledge empower you, let the story entertain you, and leave it at that. Okay, so let's go back to the early 1900s, right around the turn of the 20th century. If you got an infection back then, it was devastating, and in many cases, it was fatal. A sore throat could spread into the tonsils, turn into a deep neck infection or an abscess, and something as common as an untreated strep throat could lead to rheumatic fever, kidney failure, or neurological inflammation that no one really understood and no one had any way of treating. Even minor injuries were dangerous. A small cut or scrape, just a nick in the skin barrier, could turn into cellulitis, which was a rapidly spreading skin infection, or even full-blown sepsis, meaning a body-wide infection that would generally kill you if you didn't get treatment. And it would all come from something as simple as a shaving cut, or brushing up against a fence post and scratching your skin. Things that happen to all of us every day were basically a game of Russian roulette. You never knew whether a wound would heal normally or quietly spiral into something that would kill you, because antibiotics simply did not exist yet. Pneumonia was another major threat. In fact, in 1900, pneumonia was the leading cause of death in the United States. Pneumonia can come from different sources. Some are viral and often run their course on their own. But bacterial pneumonias or secondary infections, whether from tuberculosis or pneumococcal bacteria, were often devastating for both young and old patients. One of the most famous physicians in history, William Osler, once said that pneumonia runs its course uninfluenced by medicine. What he meant was painfully simple. Doctors just couldn't do anything about it. They tried, and most of the time without success. One approach involved giving patients serum from horses that had been exposed to the same pneumonia bacteria that was infecting the patient. But this was incredibly complicated. They didn't have fast or reliable ways to identify bacteria. They relied on these studies called agglutination studies, essentially mixing bacterial samples with serum from different horses to see which one caused clumping of the bacteria, and then hoping they found the right match. It required hospitalization, specialized labs, and time, which meant most people with pneumonia who were sick at home in the community never had access to it at all. In 1918, the Spanish flu swept through the United States, and many of the deaths were actually driven by secondary bacterial pneumonias. One insurance company, Metropolitan Life, reportedly lost $24 million in excess death benefits. Those losses made it clear that this wasn't just a medical problem. It was a societal and economic one. Companies like Metropolitan Life began pouring money into pneumonia research, funding hospital-based trials and anti-pneumococcal serum studies, all in the effort to figure out how to defeat bacterial pneumonia. Another devastating and tragically common problem was postpartum infection, also known as puerperal fever. After childbirth, the uterus is especially vulnerable, and bacteria introduced by hands or instruments could cause overwhelming infection in the mother. Back in the 1800s, a physician named Ignaz Semmelweis, who I've talked about in a previous Tribulations episode, noticed that doctors were often going straight from the autopsy room into the delivery room. When he insisted on hand washing before delivering babies, maternal infections dropped dramatically. Instead of being celebrated, he was actually ridiculed, pushed out of medicine, and eventually died in a mental institution after being violently abused, largely because he dared to call doctors out for not washing their hands. By the early 1900s, hand washing during childbirth was more common, and maternal deaths had declined, but postpartum infections were still a significant source of illness and death. And you can imagine the emotional toll. A mother dying shortly after delivery left a wound in society that was impossible to heal. Infants lost their mothers before they were even held, families were shattered, and communities carried that grief with them. Surgery was also incredibly dangerous back then. At the time, the risk of dying from infection after surgery could be as high as 50%. I perform surgeries every week, and I can't count on one hand the number of postoperative infections I've seen in the last few years. And when they do happen, they're usually minor. You give antibiotics and patients recover. But back then, even with sterile techniques developed by Joseph Lister, opening the body to the outside world was a massive risk. Surgery itself wasn't always the problem. It was the infection. Infection was the biggest threat every time a scalpel touched the skin. By the 1920s, the medical world understood that infections were caused by bacteria. Doctors knew that hand washing, cleaner hospital wards, antisepsis, and sterile surgical technique dramatically improved survival. Prevention helped, but it wasn't enough. They didn't have a pill or an injection that could safely kill bacteria inside the human body. All they could really do was try to keep the bacteria out, and that was incredibly difficult. I like to think of it as trying to keep sparks out of a dry forest. The sparks were the bacteria, and the dry forest was the human body, ready to ignite the moment a spark slipped through. That was the strategy, prevent it at all costs. But what they truly needed was treatment. They needed a way to put out the fire once it started. So this brings us to 1928. There's a microbiologist in England named Alexander Fleming, and he's working with Staphylococcus, a very common bacterium that lives on and infects the human body. Fleming is trying to answer a simple but enormously important question. Once an infection starts inside the body, is there any way to actually kill the bacteria safely? At the time, he's particularly interested in a natural antibacterial substance found in human secretions like tears and saliva. These compounds are called lysozymes, and Fleming wants to isolate and concentrate them and then use them to fight infections inside the human body. So his work is methodical and fairly routine. What he does is he grows bacteria in petri dishes, essentially creating a lawn of bacteria across the surface of the plate. Then he tests different substances by soaking small pieces of filter paper in them and placing those filter papers on the agar where the bacteria is growing. If a clear halo forms around the paper, meaning the bacteria die off in that area, it suggests that the substance has antibacterial properties. Lysozymes do show some effect, but not enough to be practical. They're difficult to isolate in large quantities, and their antibacterial power is limited. Fleming is making observations, but he's not making any breakthroughs, at least not yet. Then one weekend, he leaves his lab for a short trip. He has several plates of Staphylococcus growing on his bench, and the windows in the lab are left open. While he's gone, fungal spores drift in from the outside air and land on the plates. This is contamination, and in a laboratory setting, contamination usually means failure of the experiment. Experiments are supposed to be tightly controlled, and anything that sneaks in from the outside ruins the setup. When Fleming returns and sees the contaminated plates, they should have gone straight in the trash. But instead, he notices something strange. Where the mold has landed and begun to grow, the surrounding bacteria are completely gone. Each mold colony is surrounded by a clear halo where bacteria can't survive. Fleming calls this the zone of inhibition, and that observation stops him cold. This wasn't just random contamination. Whatever the mold was, it was producing something that actively killed the bacteria. To see if this effect was real and not just a fluke, Fleming takes the mold from the plate and grows it in a liquid broth. Once the mold has been cultured, he filters the broth. The filter removes the mold itself, but anything that the mold has secreted into the liquid passes through the filter. Now he has a clear solution with no mold in it, just whatever substances the mold has produced. He takes that filtered broth and he tests it on Staphylococcus. The result is unmistakable. The bacteria are completely killed. The mold turns out to be Penicillium notatum. Fleming publishes his findings in 1929 and names the antibacterial substance Penicillin. This is the discovery we all hear about, the accidental mold, the contaminated plates, and the lucky observation that changed medicine forever. But what we almost never hear is what happened next, which is essentially nothing. After Fleming publishes his paper, progress stalls. Penicillin doesn't move towards clinical use. It doesn't become a drug. It just sits there in the scientific literature. Fleming is a brilliant microbiologist, but he doesn't have the tools, the biochemical expertise, or the infrastructure to turn this fragile substance into something that can be purified, produced, and safely given to patients. So penicillin remains an academic curiosity for nearly a decade, and it takes something much bigger than scientific curiosity to bring it back to life. It takes a world war. So Fleming published this paper in 1929, and 10 years later, in 1939, World War II begins. The world was barely recovered from World War I, and one of the lessons everyone had learned the hard way was that soldiers didn't always die from dramatic battlefield injuries. They died many times from infections. A small piece of shrapnel, a scrape, a bullet wound, even a dental infection could turn into something lethal. These were young men who were exhausted, malnourished, stressed, and living in brutal conditions. And once an infection set in, it could disable or kill them just as effectively as enemy fire. Military leaders understood something very clearly. If they could keep soldiers alive and fighting by controlling infection, they would gain a massive advantage in the war. A drug that could kill bacteria inside the body was not just a medical breakthrough, it was a strategic weapon. That realization is what leads the United Kingdom to launch what became known as the Oxford Penicillin Project. And this is where three of the most important and least recognized figures in medical history enter the story. Most people know the name Alexander Fleming, and that's usually where the story ends. But Fleming made an observation and published a paper. He did not turn penicillin into a usable drug. That credit belongs to three men whose names are far less familiar. The first is Howard Florey. Florey was a pathologist who had recently been appointed professor of pathology at Oxford, and he had established a laboratory that would become the birthplace of clinical penicillin. And here's the key. He was not the person who could solve the chemistry or the manufacturing problems by himself. But what he did know was how to build a team, how to direct a mission, and how to move an idea from possibility to reality. In many ways, Florey was the commanding general of the penicillin effort. The first person he needed was a biochemist, and that led him to Ernest Chain. Chain was a German-born Jewish biochemist who had fled Nazi Germany as a refugee. For him, this work was personal. He was brilliant in exactly what the project needed. Penicillin turned out to be an extraordinarily fragile molecule. Heat it too much, shift the pH too quickly, or handle it carelessly, and it simply fell apart. Every attempt to isolate it risked destroying the very thing you were trying to save and produce. Chain's role was to develop the biochemical assays and the purification methods that could extract penicillin from the fungal broth while keeping it intact. The third key figure was Norman Heatley, a young scientist with a rare talent for inventing practical tools. Chain understood the chemistry, but chemistry alone was not enough. They needed new equipment, custom-built devices that simply did not exist yet. And Heatley was the person who could imagine them and then build them. He created cylinder plate diffusion assays that allowed the team to quickly test whether penicillin had survived each purification step. He designed methods to extract penicillin into solvents and then back into water again. Most importantly, he developed specialized culture vessels that allowed the penicillin mold to grow efficiently while minimizing contamination. The mold was grown almost like a living mat, floating on the surface of liquid broth. This is similar to how kombucha forms a thick layer on top of tea. But contamination was a constant threat. If something unwanted got in, the entire batch could be completely ruined. Heatley developed ceramic vessels that allowed the mold to grow on top of the broth, sealed from the outside world, with small ports that allowed the researchers to remove spent broth and replace it with fresh media without exposing the culture to the outside world. These designs were crude, improvised, and absolutely brilliant, and they helped make the mission possible. Working together, Florey, Chain, and Heatley finally managed to isolate penicillin from fungal broth in usable form. The quantities were tiny, far too small for widespread treatment, but this was a massive leap forward. Unlike Fleming's original crude broth, which could never be used therapeutically, this was penicillin dissolved in pure water, stable enough to test, and ready to be given to living organisms. For the first time, penicillin was no longer just a laboratory curiosity. It was becoming a real drug. The first thing they did was start with animals. They infected mice with a lethal bacterial infection, one they knew would reliably kill them. Then they split the mice into two groups. One received no treatment at all. The other group received their newly isolated penicillin. The results were unmistakable. The untreated mice all died. The mice that received penicillin lived and went on as if nothing had ever happened. It was the first clear proof that they were onto something enormous. Those results were exhilarating, but Howard Florey stayed grounded. He was encouraged, but he was also realistic. He made a point that brought everyone back to reality. Mice are one thing, but humans are 3,000 times larger. Treating a mouse was a milestone, but it wasn't the finish line. They needed to treat a human, and beyond that, they needed to treat thousands of humans. In 1941, they got their first chance. A 43-year-old police officer named Albert Alexander had scratched his face on a rose thorn. That simple scratch turned into a catastrophic infection. It spread rapidly, and by the time he reached the hospital, he was dying. There was no realistic chance that he would survive. So they made the decision to use penicillin on him. At the time, penicillin was dissolved in sterile water and injected into the muscle. Within 24 hours, the change was dramatic. A man who had been on his deathbed was suddenly awake, eating, and clearly improving. It almost didn't even make sense to them. Someone who should have died from overwhelming infection was visibly coming back to life. It was nothing short of a miracle. But there was a problem. Penicillin doesn't last long in the body. It's rapidly cleared by the kidneys and excreted in the urine. And in the Oxford lab, their supply was vanishing fast. They quickly ran out of penicillin, even though Alexander was clearly responding and needed to continue his treatment to survive. So they improvised. Doctors began collecting his urine, jumping on bicycles, racing across town to a lab where penicillin was painstakingly extracted and then brought back to be injected into Alexander again. Penicillin was treated like gold dust because at the moment, it was the rarest and most valuable substance on Earth. For a short time, this worked, but soon the amount of penicillin they could recover from his urine began to fall. The supply dried up completely. Without continued treatment, the infection returned. Albert Alexander relapsed and died in March of 1941. His death was tragic, but it proved something that the world desperately needed to know. Penicillin worked in human beings. It was effective, and it was well below any toxic threshold. The problem wasn't safety or efficacy. The problem was supply. And that realization changed everything. So now you've got Howard Florey, Ernest Chain, and Norman Heatley. They've figured out how to isolate penicillin. They've shown that it works in animals. They've shown that it can work in human beings. But despite all that progress, despite all the ingenuity and all the new equipment they built, they still couldn't make enough penicillin to fully treat even one patient. The science was there, but the scale was not. That's when Florey makes a critical decision. With government permission and real urgency behind him, he decides to take penicillin to America. And the reason is simple. At that moment in history, if you needed to manufacture something in massive quantities, America was the place to do it. So under the shadow of World War II, with the Blitzkrieg underway and bombs falling on London, Florey and Heatley leave England for the United States, carrying vials of penicillium spores in their pockets. Heatley is deeply worried during the journey. He figures that if they're captured, this isn't just luggage. This is essentially a state secret that could be seized and used by the enemy. They aren't soldiers and they can't protect the vials, so they come up with a backup plan. They take penicillin spores and coat the inside linings of their jackets with them. That way, even if the vials are lost, even if the worst happens, like they're killed or something like that, the spores could still be recovered by swabbing the fabric and culturing them. Penicillin would still make it to America one way or the other. So they make it across the Atlantic and they arrive in Peoria, Illinois, which is home to the USDA Northern Regional Research Laboratory. And this is exactly where they need to be. These scientists are not thinking in terms of petri dishes. They're experts in large-scale agricultural fermentation. If anyone knows how to turn a fungus into an industrial product, it's these guys. Once the Americans review the process, they immediately see the bottlenecks. The first problem is scale. Heatley's culture vessels work, but they're tiny. Researchers are siphoning off small amounts of broth from hundreds of containers just to harvest minuscule amounts of penicillin. That was never going to be enough. They needed massive vats. The second problem is yield. The penicillium mold they brought from England produces penicillin, but not very much. Even if they scaled up production, they still wouldn't get enough output. they needed a better strain, one that naturally produced far more penicillin. So with those goals in mind, the work in Peoria begins. This is where a woman named Mary Hunt enters the story. She works at the lab and spends time collecting samples because at that point, the researchers are looking everywhere for molds that might produce more penicillin. One day, she finds a moldy cantaloupe at a local market. She recognizes the mold, brings it back to the lab, and has it tested. It turns out to be a game changer. The strain from that cantaloupe produces dramatically more penicillin. By some accounts, up to 1,000 times more than the strain Florey and Heatley brought from England. This mold becomes the backbone of penicillin production for the Allies in the war. Mary Hunt later earns the nickname Moldy Mary, and her cantaloupe quietly helps change the course of the war. So now they have a better mold, but they still need a way to grow it at scale. That's where the industry steps in. One of the companies involved, Pfizer, proposes something bold. They take massive vats normally used to brew beer and adapt them for what's called deep tank fermentation. Instead of letting the fungus sit on the surface, they suspend it in a constantly mixed, oxygenated broth. They carefully control oxygen levels, pH, and foam, allowing the fungus to thrive through the entire tank. Instead of a thin layer of mold on top, now they have massive volumes of actively growing fungus producing penicillin around the clock. The results are staggering. The new mold strain increases penicillin production by roughly 1,000-fold, and deep tank fermentation multiplies that output by another 250x. Something that once seemed impossible suddenly looks achievable. For the first time, mass production of penicillin is within reach. Then, in 1942, while all this work on mass production is still underway, another pivotal moment arrives. A young woman named Ann Miller develops septicemia after a miscarriage-related infection. She is rapidly dying from overwhelming sepsis. And it's worth pausing here and mentioning something. People are still dying of infections everywhere at this point. These patients aren't rare. What's rare is attention. Fate shines a spotlight on one person while countless others suffer the same way in the background. Her physician knows about penicillin and asks the US government for permission to use it. And that's how precious penicillin still is at this moment. It's not a drug, it's a controlled resource. The War Production Board, which oversees penicillin production, has to approve its use. They grant permission for her doctor to use about a tablespoon of penicillin. And that's what it comes down to cure this woman. The penicillin is dissolved in purified water and administered in several injections. And it works completely. Ann Miller recovers and goes on to live a full life, finally dying in 1990 at the age of 99. And with that, the United States finally has its proof. Penicillin isn't just a laboratory experiment. It's a real life-saving technology that can change the course of humanity and, importantly, change the course of the war. But here's the sobering part. That single tablespoon of penicillin represented roughly half of the entire U.S. supply at the time. Even while companies like Pfizer and others are already scaling up production using deep tank fermentation and improved mold strains, saving one woman's life consumed half of what the country had at the time. And that creates a moment of clarity. This is 1942, and D-Day is coming in 1944. A massive invasion of Europe is being planned, and with all the effort so far, the United States has barely enough penicillin to treat 1 or 2 people. That's not even close to what they're going to need. They don't need dozens of doses. They need millions. So the US government steps in and does something extraordinary. It convenes pharmaceutical leaders and makes penicillin a national priority. Trade secrets are suspended, antitrust concerns are set aside, and the message is simple. Work together. Share everything. Every improvement, every technique, every breakthrough gets shared immediately. This is bigger than any one company, and the industry responds. American manufacturing power, scientific ingenuity, and wartime urgency all come together. By June 6, 1944, D-Day, 2.3 million doses of penicillin have been produced and prepared for the invasion. We often hear that the atomic bomb was the most important weapon in World War II. And in the Pacific, that may have been true. But in Europe, the Allies had another superpower. They had penicillin. Penicillin kept soldiers alive. It turned what had once been fatal wounds into treatable infections. It allowed rapid recovery and return to duty. Quietly and powerfully, penicillin reshaped the battlefield. In doing so, it helped change the outcome of the war. So the war ends, and what remains is penicillin. And penicillin goes on to change the world. We take antibiotics for granted now. Even if we get a small infection, sometimes even when we're not entirely sure we have one, we reach for antibiotics without thinking twice. They are so deeply embedded in modern medicine that almost every person alive today has relied on them at some point. They're not a niche technology. They are foundational. After the war, antibiotics quickly became routine. Every hospital, every family doctor's office, every clinic across the country had them. Infections that once terrified physicians and families alike, things like strep throat, minor cuts, post-surgical infections, and postpartum infections, suddenly became treatable. What had once been life-threatening became manageable and often trivial. But penicillin also sparked a much bigger question. If one accidental mold growing on a cantaloupe could produce something this powerful, what else was out there? Microbes are constantly competing with one another. They don't have immune systems like we do. Instead, they rely on chemistry. They make compounds to inhibit, injure, or kill other competitors. Penicillin was just one example of that chemical warfare. Once scientists realized this, they went looking for more, and they looked everywhere. They collected microbes from farms, forests, riverbanks, compost piles, and soil samples, and they used the same basic assays that Fleming had stumbled upon in 1928, which was growing organisms side by side and watching to see which ones killed the others. When they found the microbe that could suppress another, they isolated it and explored whether that chemical could be used safely in humans. This search turned into a scientific treasure hunt. Out of that search comes streptomycin, which finally allows doctors to treat tuberculosis, one of the great killers of the 20th century. Then comes tetracyclines, chloramphenicol, erythromycin, vancomycin, cephalosporins. All of them follow the same basic scientific model that was first popularized by Fleming and later systematized by a scientist named Selman Waksman at Rutgers, who helped turn antibiotic discovery into a disciplined scientific process. Miracles were being pulled from the soil, from forests, from moldy fruit left on the countertop, and medicine was transformed. A scratch or a simple infection was no longer a death sentence. But with that success came a new problem: antibiotic resistance. Microbes evolve constantly. Just as they develop weapons to kill one another, they developed defenses to survive. Even in the 1940s, Ernest Chain had already identified enzymes like beta-lactamase, which could break down penicillin. That was the first warning that bacteria were already learning how to fight back. The same thing happened when streptomycin was first used to treat tuberculosis. Resistance emerged quickly, forcing doctors to use multiple antibiotics at the same time to prevent bacteria from adapting. That challenge still has not gone away. Overuse, inappropriate prescribing, incomplete courses, underdosing, and widespread use of antibiotics in agriculture have all accelerated the problem. We now face bacteria that have learned how to bypass many of the tools that once saved modern society from infection. Globally, antibiotic-resistant infections are estimated to be associated with more than 1 million deaths per year. In the United States alone, around 35,000 people die every year from infections that no longer respond to available antibiotics. This is not theoretical. It's already happening to us. And for decades, we kept discovering new antibiotics. We searched relentlessly, and we were productive. And the truth is, we have not run out of microbes. The potential pool of undiscovered antibiotic compounds is still out there, and it's enormous. But what has changed is the incentive to discover them. Antibiotics are short-course drugs. You take them, the infection clears, and you stop. From a business perspective, that makes them far less attractive than chronic medications that patients take for decades. As a result, far less money flows into antibiotic development than into drugs for long-term conditions. The antibiotic pipeline of development has thinned, even as resistance continues to rise. Will we reach a point where common infections are untreatable again? I think that's unlikely, but it's not impossible. And that means we have a responsibility. Using antibiotics wisely matters. Taking them only when they're truly needed matters. Finishing prescribed courses of antibiotics matters. Treating a viral cold with antibiotics doesn't help you, but it does help spread resistance. When we misuse these drugs, we don't honor the extraordinary effort, sacrifice, and ingenuity that brought them into the world in the first place. So that's something that's super important to keep in mind. Now, that being said, I do want to mention a new frontier on the horizon of our war against infections, and that's bacteriophages. Just as humans get viral infections, bacteria do too. Bacteriophages are viruses that infect bacteria and only bacteria. They attach to specific bacterial cells, inject their genetic material, replicate inside, and often burst the cell open, moving on to the next target. Our own GI tracts are full of bacteriophages where they play a major role in shaping the microbiome. On a global scale, bacteriophages even regulate massive bacterial blooms in the oceans, which are cycles so large they can be seen from space. And because they don't infect human cells, bacteriophages are now being studied as potential therapies for infections that no longer respond to antibiotics. They're not a replacement for antibiotics yet, but they may become a critical backup when our traditional tools fail. And I think it's very exciting to think about the next frontier of antibacterial therapy. So to wrap it up, the discovery of penicillin and the antibiotics that followed may be among the greatest medical breakthroughs in human history. It's a story worth knowing and a legacy of innovation we all need to respect. I think that when we understand how precious these discoveries were and how hard won they were, we're far more likely to use them wisely. So I hope you enjoyed that story. This marks the end of season 1 of the Dr. Kumar Discovery. I'll be taking a short break and we'll be back in February or March with a new season that includes interviews, deep dives, and more storytelling. Tribulations will likely spin into its own feed, focusing purely on medical history and storytelling, while the Dr. Kumar Discovery will continue to focus on more clinical and science-focused episodes. We started this journey in April, and I've released about an episode every week since then. It's been an incredible 8 months. I've learned a tremendous amount, and I've loved bringing you along on that journey. During the break, you can still find me on YouTube, Instagram, and TikTok, where I'll be posting short videos that are informative and entertaining. And when the new season starts, we'll open up a whole new treasure chest of discoveries together. So until then, stay curious, stay skeptical, and stay healthy, and I'll see you soon. Cheers.